our corner of the universe holds a secret that went unnoticed for decades. The region around our galaxy is far emptier than anyone had assumed. Astronomers long believed that the cosmos, although clumpy on small scales, would smooth out and appear uniform when viewed over immense distances. But measurements of galaxies in our vicinity told a more troubling story. Researchers mapping nearby space counted fewer galaxies than standard cosmological models predicted. The deficiency was not subtle. It revealed that the environment we occupy contained significantly less matter than the theoretical average. This persistent underdensity, once dismissed as noise or survey error, has steadily proven to be real. And because our galaxy lies at the heart of this mystery, every major cosmic observation we make is filtered through a biased location. The discovery of the void started with what seemed like small inconsistencies. Some galaxy surveys showed strange sparsity in multiple directions. Redshift measurements revealed odd velocities for nearby structures, movements too strong and systematically outward to be explained solely by cosmic expansion. Astronomers suspected something was off but resisted the idea that our entire region might be anomalous. The foundational principle of cosmology, the idea that no observer's location is special, strongly discouraged such a conclusion. Yet as mapping techniques improved and new datasets accumulated, the same unsettling pattern continued to emerge. We live inside an enormous bubble of low density. The full implications did not become clear until researchers like Ryan Keenan and Amy Barger began comparing galaxy counts over progressively larger distances. Their results demonstrated that our local universe contains roughly 20% less matter than it should. This was no small statistical fluctuation. It represented a deviation so expansive that it covered hundreds of millions of light-years. Follow-up analyses refined the structure's dimensions, revealing that the underdense zone extends nearly 1 billion light-years across. Named after Keenan, Barger, and Cowie, the KBC void is not just large, it is unprecedented. Typical voids in the cosmic web are a fraction of its size. When astronomers speak of 1 billion light-years, they refer to expanses vast enough to contain tens of thousands of galaxies. That our own galaxy lies within such a rare structure forces a complete re-evaluation of assumptions that once seemed untouchable. The more researchers studied the region, the more it became evident that we're not just near the edge or skimming its border. Instead, we reside comfortably inside this emptiness, influenced by the gravitational imbalance it creates. The discovery challenges a long-standing belief that space, when averaged over large volumes, behaves uniformly. This doctrine supported nearly every calculation in modern cosmology. It allowed scientists to infer the universe's age, shape, and fate without worrying about positional biases. But if we occupy a region drastically unlike the average, then the values we measure, expansion rate, density, curvature, are distorted by our specific vantage point. It is like trying to judge the climate of Earth while living permanently in Antarctica. You may be convinced the entire planet is cold, when in fact you simply occupy a particularly frigid region. The existence of this enormous void throws into doubt the universal applicability of our local measurements. Living inside an underdense region has real consequences. With less mass surrounding us, gravity here exerts weaker restraint on cosmic expansion. That means objects around us appear to recede faster than they would in denser regions. The effect makes the universe look as if it is expanding more rapidly than theory predicts, giving rise to tensions between local observations and predictions from the early universe. This inconsistency, especially regarding the measured Hubble constant, has become one of the most pressing problems in cosmology. The void offers one of the few explanations that does not require rewriting the laws of physics or quantum mechanics. Instead, it simply states that our measurement yardstick is biased because we live in an unrepresentative neighborhood. Over time, evidence for the void accumulated from multiple independent sources. Peculiar velocities of galaxies, gravitational lensing data, and deep-field galaxy surveys all pointed toward the same conclusion. A massive underdensity encompasses the Milky Way. The surprising part is not only its scale, but how long it took humanity to notice. We had been swimming inside a cosmic desert without recognizing that the ocean lay much farther away. Its presence remained hidden because the emptiness around us shaped the very tools used to detect it. Only after comparing large datasets from different techniques did the truth become clear. The universe is not as uniform as we assumed, and we are living in one of its most extraordinary voids. The discovery marks a turning point in our understanding of the cosmos. Once, we imagined ourselves occupying a typical location with a typical view of the universe. Now it appears our vantage point may be deeply exceptional, dramatically altering the appearance of everything seen from here. The KBC void forces us to ask whether the universe's truths can be uncovered from such a strange and biased seat. And it demands a new humility. Perhaps our cosmic home is not the standard against which the universe should be measured, but an outlier that has misled us for far too long. The presence of such an immense void surrounding us introduces a profound challenge to the foundational assumptions on which modern cosmology was built. For over a century, scientists have operated under what is called the cosmological principle, the idea that on sufficiently large scales, matter is distributed uniformly throughout the universe, and that no location is special or privileged. This principle emerged not merely from philosophical modesty, but from observational necessity. It allowed cosmologists to generalize their local measurements to the entire cosmos, to model the expansion of space, and to derive the theoretical framework of the Big Bang. Yet the KBC void calls all of this into question. If we reside in a region far emptier than average, then our measurements of density, expansion, and even time evolution may not represent the universe as a whole. It means our cosmic perspective is distorted by circumstance. Imagine standing atop a hill and believing the entire landscape slopes downward, unaware of valleys and mountains beyond your sight. That is precisely the effect of being positioned inside a massive void. The laws we infer from local observations might hold true only for this peculiar patch of universe. The scale of the void intensifies the problem. Normal voids, common features in the cosmic web, are relatively small, spanning 30 to 150 million light-years. They form naturally as gravity pulls matter into clusters and leaves behind empty pockets. But a void approaching 1 billion light-years across lies at the extreme edge of what current models expect. In simulations of structure formation, a void of this magnitude is possible but exceedingly unlikely. The standard LCDM model, which combines general relativity with dark energy and dark matter, predicts that a void of such depth and size should be so statistically improbable that encountering one would be akin to winning a cosmic lottery, or more accurately, losing one. The argument becomes especially concerning when we consider our exact placement. Not only do we dwell inside this unusual emptiness, but we are positioned remarkably near its centre. If the universe were populated with such voids everywhere, the odds of us sitting near the middle of one might feel less dramatic. But if the KBC void is one of the largest in the known universe, the likelihood of being located where we are is astronomically small. It is as if humanity built its only observatory at the bottom of a colossal crater and then declared that flat plains must be rare. Cosmologists have always resisted ideas that put humans in any kind of cosmic spotlight. The Copernican principle, the notion that we do not occupy a privileged position, serves as a philosophical backbone to science. But the discovery of the void places tension on that belief. To accept the KBC void is to accept that we live in a region highly atypical compared to the universe at large. Either we have an astoundingly improbable position, or our understanding of cosmic structure needs modification. In response, some scientists have attempted to downplay the void's significance by suggesting that underdensities of different shapes and scales might combine to produce misleading observational effects. Others propose that we may be overestimating the void's volume due to the limitations of sampling nearby galaxies. After all, local surveys inherently suffer from measurement bias. The closer something is, the more precisely we can measure it, but also the more its irregularities affect our conclusions. Despite skepticism, new observational methods consistently validate the underdensity. Whether through galaxy counts, cosmic microwave background imprints, or velocity flows, the evidence keeps circling back to the same reality. The region around the Milky Way lacks the expected amount of matter. So the question grows sharper and more urgent. How did we end up here? If the void is genuine and its size accurately measured, then some fundamental principle must be reconsidered. Either the universe is far more inhomogeneous on large scales than previously assumed, or the probability of our existence in such a region needs a compelling explanation. Neither option is comfortable. One path leads to rewriting cosmological theory. The other edge is dangerously close to anthropic reasoning. suggesting that our unusual location is necessary for intelligent life to arise or for sophisticated observation to occur. This idea triggers philosophical alarms because it seems to place humanity back into a special category, a position science has spent centuries escaping. Yet the KBC void refuses to vanish under scrutiny. Instead, it stands as a blind spot we have only just recognized. It forces cosmologists into a choice: cling to the assumption of universal uniformity despite mounting contradictions, or acknowledge that the universe may be more uneven, more intricately structured, and more unpredictable than the smooth equations of early theory implied. The existence of such a void does not prove our uniqueness in a metaphysical sense, but it certainly demands a reconsideration of what typical means in the cosmos. Maybe large-scale uniformity is merely an approximation, useful but not absolute. Or perhaps we have stumbled onto evidence that the universe contains rare anomalies, and that by chance or necessity we inhabit one. Whatever the answer, the KBC void transforms our simple cosmic map into a far stranger and more complex terrain, where assumptions crumble and new mysteries rise from the emptiness that surrounds us. As researchers dug deeper into the properties of our surrounding void, they realized its enormity was unlike anything previously documented. The KBC void is not just an empty region, it is an underdensity with defined structure, measurable gradients, and dynamic influence on the galaxies embedded within it. The contrast between its sparse interior and the denser cosmic filaments beyond creates noticeable gravitational effects, altering the flow of matter and reshaping the local expansion of space. To grasp the true strangeness of this structure, one must compare it with other voids catalogued throughout the universe. The cosmos is filled with a network resembling a three-dimensional sponge or web. Its filaments of galaxies form at the intersections of gravitational collapse, leaving behind pockets voids where matter failed to cluster. These voids are usually surrounded by walls and threads of galaxies marking boundaries, like the seams of an intricate cosmic fabric. In this context, the KBC void stands out because of both its size and depth. While average voids stretch across dozens of millions of light-years, ours spans nearly 1 billion. Many smaller voids can coexist like bubbles in foam, but a single underdensity of this magnitude is astonishing, dwarfing the common structures that populate the cosmic web. Some cosmological simulations allow such a giant void to emerge statistically, but they estimate that the likelihood of a galaxy like ours forming so close to the center of one is tiny, far less than 1%. Unique does not even begin to describe it. The edges of the void reveal even more peculiar behavior. As one travels outward in any direction, the number of galaxies increases sharply, marking a boundary where the underdense interior transitions to a region of higher mass concentration. This sudden shift suggests the void is not an amorphous gap but a massive spherical cavity, defined by clear density contrast. That near-spherical shape deepens the mystery, for nature rarely sculpts such symmetry on cosmological scales without a guiding mechanism. Yet, our void seems to maintain this geometry with surprising consistency. The fact that we appear positioned almost centrally makes the scenario even harder to dismiss as coincidence. Astronomers like to remind themselves that Earth does not sit at the center of anything, neither the solar system, the Milky Way, nor the universe. But in the case of the KBC void, our location challenges that narrative. If the underdensity were irregular, stretched, or lopsided, it might be easier to accept our accidental placement inside it. But a symmetric bubble with our galaxy near the middle looks suspiciously tailored, a cosmic bullseye with the arrow stuck in its heart. Some scientists argue that our presence here could skew our perception of the void's true shape, making its symmetry appear greater than it is. The difficulty lies in measurement. To map the void fully, we must observe galaxies farther away, but our vantage deep inside the emptiness reduces contrast and complicates the task. Despite uncertainties, new surveys continue reinforcing the void's scope. Infrared galaxy maps, advanced redshift catalogues, and radio telescope data all coalesce into the same macrostructure. What once seemed an observational artifact has become a defining feature of our cosmic neighborhood. The uniqueness of the void implies consequences beyond spatial distribution. In the cosmic web, matter flows slowly but inexorably, from emptier zones toward denser ones. The underdensity exerts an outward push due to its relatively weaker gravitational pull, meaning galaxies near its edge appear to accelerate away from the center, faster than uniform expansion alone predicts. These peculiar velocities were once puzzling irregularities, but now they signify the hidden presence of the void-shaping motion. This outward flow is not chaotic but systematic, radiating in all directions, hinting again that we occupy a central region. The deeper cosmological models struggle to incorporate such a dramatic structure. Some hypotheses suggest the void may be part of a larger chain or network of lesser-known underdensities. Others consider the possibility that the void formed from an unusually large primordial fluctuation in the early universe, an island of low matter density seeded during inflation. If so, its existence becomes a clue pointing toward deeper questions about the conditions predating the cosmic microwave background. How could quantum noise stretched across space have yielded something so persistently empty? Another perspective views the void as a potential key to resolving the Hubble tension, the stubborn disagreement between the locally observed expansion rate and the rate predicted based on early universe physics. If our region is underdense, galaxies appear to recede faster when we measure them from here, meaning the expansion rate we infer is artificially inflated. The local void thus might explain why nearby measurements of the Hubble constant are consistently higher than those calculated using the cosmic microwave background. This explanation offers an elegant solution, sparing the need for exotic new physics or rewriting the nature of dark energy. Yet not all cosmologists are ready to embrace such an answer. Accepting the void as the reason for the discrepancy means acknowledging that we inhabit a deeply atypical place. The philosophical discomfort remains. Have we once again found ourselves in a location that seems special against all expectation? The scientific community finds itself walking a razor's edge between two daunting possibilities. Either our models of structure formation are missing critical elements that could naturally produce such a void, or the universe is telling us that rare locations exist and that we happen to call one of them home. The KBC void sits as a silent judge over our assumptions, waiting for us to decide whether to cling to theoretical elegance or face the unsettling reality that the cosmos might not play by the rules we wrote for it. To fully appreciate the significance of our cosmic environment, we must understand how our galaxy is situated within the larger structures that organize the universe. On the smallest scales, the Milky Way and Andromeda dominate a gravitationally bound cluster known as the local group. It contains a few dozen smaller satellite galaxies arranged in a dance determined by their mutual attraction. But this cluster is only a modest component of a far grander structure. Beyond the local group lies a vast territory called the Laniakea supercluster, a sprawling region that stretches roughly 500 million light-years across and contains around 100,000 galaxies. Its name, derived from Hawaiian, means immense heaven, and the term is fitting. Laniakea is a cosmic continent, a gravitational domain in which matter flows toward a central convergence point known as the Great Attractor. It is this gravitational basin that defines the supercluster's boundaries, much like rivers draining into a single ocean. But even this enormous structure does not fully describe our situation. Laniakea, including the Great Attractor region, lies embedded in the expansive emptiness of the KBC void. In maps of the cosmic web, this juxtaposition is startling. Our supercluster, packed with filaments and clusters, appears like a lush, fertile landscape surrounded by an immense and barren desert. For billions of years, matter has been streaming along cosmic highways, converging toward denser hubs such as the Great Attractor. This flow indicates that, despite being inside a void, our sector has enough mass concentration to exert a gravitational pull, strong enough to influence the motion of galaxies far beyond the local group. Visualizing this structure reveals a dramatic picture. Galaxies following curved paths like rivers, bending toward a deep valley carved into the underlying gravitational field. These velocities cannot be explained by universal expansion alone. Instead, they illustrate the local topography of gravity where mass collects, motion follows. The Great Attractor sits approximately 150 to 250 million light-years away, and though much about it remains obscured by the dense plane of our own galaxy, its gravitational influence is undeniable. Observational data show that the Milky Way, Andromeda, and countless neighbouring galaxies are rushing toward this hidden mass concentration at hundreds of kilometres per second. The concept becomes more intriguing when one considers that the local expansion of space inside the void is slightly faster than average. This means that while the void's emptiness reduces gravitational slowing, the dense region of the Great Attractor simultaneously tugs inward, creating a dynamic tension. The supercluster, then, becomes a kind of archipelago-dense islands of matter adrift in a sea of accelerating emptiness. Even though Laniakea occupies a region with less matter than the universal norm, the structure is still cohesive because of its internal gravitational network. However, the long-term fate of this network remains uncertain. The KBC void's influence might one day overcome the gravitational pull that currently binds the supercluster. Over immense timescales, dark energy and local underdensity could stretch the structure until the flow toward the great attractor slows, stops, and reverses. At that point, Laniakea would cease to function as a unified supercluster. Each cluster and galaxy group would follow its own path deeper into the void's accelerated expansion. This outcome highlights the delicacy of our cosmic placement. We are close enough to dense regions to remain gravitationally connected, yet surrounded by enough emptiness to be influenced by accelerated outward motion. It is a temporary balance, one that may eventually shift toward isolation. Our location within Laniakea also shapes our observations. Looking outward, we see the universe filtered by the gravitational wells of the supercluster's structure. We experience motion relative to the cosmic microwave background, manifesting as a dipole anisotropy evidence of our drift toward the great attractor. This drift gives away our position in the gravitational landscape. Without the KBC void, our velocity might be slower, our measurements more aligned with the uniform cosmic expansion. The void exaggerates the speed with which galaxies move relative to each other in our region, complicating the interpretation of redshift, the measure cosmologists use as a clock and ruler for the universe. The mapping of Laniakea was a breakthrough in understanding this environment. By analyzing velocity flows rather than relying solely on galaxy positions, researchers identified the gravitational reach of the supercluster more accurately. They discovered that what defined Laniakea was not spatial boundaries in the traditional sense, but the direction of motion matter moving toward the same attractor belongs to the same structure. This new way of defining superclusters respects the true physics of cosmic organization. And yet, even this impressive domain appears as a minor feature when viewed against the colossal background of the void. It is like discovering that the continent on which you live, though vast and significant, is actually a modest plateau suspended in a gargantuan abyss. The void frames everything, influencing all the structures within it and dictating the future paths of galaxies. Therefore, our cosmic address cannot be understood without acknowledging both the fertile richness of Laniakea and the profound emptiness enveloping it. The fact that we reside in a gravitational stronghold surrounded by a nearly billion light-year expanse of sparsity is more than a map coordinate, it is a defining feature of existence. It affects the light we see, the speed at which we travel, and the conclusions we draw about the nature of the universe itself. To understand the cosmos properly, we must first understand the strange neighborhood we call home. The influence of the KBC void extends beyond simple spatial emptiness. It directly impacts the movements of galaxies and the measurements cosmologists rely on to decode the universe's history. Within this vast underdense environment, the gravitational pull is weaker because mass is scarce. As a result, cosmic expansion proceeds more freely, causing galaxies inside the void to drift away from each other faster than they would in denser regions. This phenomenon manifests as peculiar velocities motions that deviate from expectations based solely on the Hubble flow. When astronomers first observed these irregular velocities, they struggled to determine whether the galaxies themselves were behaving strangely, or whether the expansion rate in our local region was inflated. Over time, patterns emerged that made the answer unavoidable. Galaxies around us are consistently accelerating outward from a central region aligned with our location, implying that we lie near the heart of an expanding bubble of underdensity. That radial symmetry is one of the strongest indicators that the void is not merely a patchwork of minor fluctuations. Instead, it is a coherent structure influencing motion on scales large enough to redefine local cosmology. This outward drift does not appear chaotic but organized, like the spreading ripples of a pebble dropped into a pond. Our galaxy, along with many others in the local sheet and local volume, participates in this motion. It is important to note that cosmic expansion alone cannot explain such uniform outward velocities. Something additional, something structural is shaping the universe around us. The observed peculiar velocities arise from the interplay between lower gravitational resistance inside the void and stronger attraction toward dense external regions. Galaxies near the void's rim feel the tug of massive structures outside, accelerating them outward relative to the central emptiness. Meanwhile, galaxies closer to the center, like our own, remain somewhat suspended in a region where outward acceleration dominates, but gravitational tethers to surrounding mass still exert influence. This delicate balance reveals a dynamic system, a gravitational push and pull scenario sculpted by unequal mass distribution. From our perspective, it creates the illusion that the universe is expanding faster here than elsewhere. That illusion becomes problematic when we attempt to measure fundamental cosmic parameters. For instance, the Hubble constant, which quantifies the rate of expansion, relies heavily on redshift measurements of nearby galaxies. If redshifts here are boosted by local underdensity, then our inferred value becomes artificially high. This inflation contributes to what is known as the Hubble Tension, a persistent disagreement between expansion rates predicted by early universe physics and those measured in the local universe. The void provides an elegant explanation. We live in a region where expansion is naturally faster, so our measurements do not represent the cosmic average. Peculiar velocity surveys have strengthened confidence in the void's significance. Observations of galaxy clusters, motions of local group members, and mapping of cosmic flows have built a consistent narrative. We see galaxy streams diverging outward from our region, even as others converge toward denser hubs like the Shapley supercluster or the Great Attractor. Ignoring the void leads to errors in interpreting these flows and in estimating distances beyond our immediate environment. Moreover, the void impacts not just galaxy motion but also gravitational lensing, a technique used to detect mass by observing how it bends light. Because this area contains less mass, lensing effects are weaker here than expected. The lack of distortion confirms the absence of matter that theory demands should be present. Each independent line of evidence peculiar velocities, galaxy counts, redshift discrepancies, weak lensing aligns to reveal the same structure. This convergence of data makes the void more than an abstract mathematical correction. It becomes a physical reality shaping our understanding of everything from our galaxy's trajectory to the deep time fate of the cosmos. Yet, despite the mounting evidence, the idea that our position is so central within the void continues to stir discomfort. If the void were real, but we dwelled near its edge, the implications for cosmology would be less severe. But occupying a nearly central location suggests observational bias of the highest order. It implies that when we point telescopes outward, we are gazing from an environment that is fundamentally atypical-like, trying to deduce the geography of Earth while living in a remote and extreme desert. Our situation forces a question that cosmology has long resisted asking. What if the view from our location is simply not representative of the universe at large? In the past, we have repeatedly discovered that assumptions about our cosmic significance were misguided. We learned that Earth is not the center of the solar system, that our galaxy is not the entire universe, and that no special direction or orientation defines a universal reference frame. The void tests this tradition of humility. It suggests a new kind of exceptionalism not philosophical, but statistical. We do not occupy the center of all things, but we do appear to reside in the center of one very unusual phenomenon. That fact alone compels us to reconsider how we interpret the cosmos. For if motion, distance, and expansion are all influenced by the emptiness surrounding us, then our measurements must be corrected to avoid drawing conclusions that are distorted by our peculiar vantage point. The KBC void's most disruptive legacy may therefore be its challenge to our certainty. It reveals that reality is shaped not only by what exists but by where we stand. In recognizing the power of this local underdensity, cosmology moves closer to acknowledging the complexity and asymmetry of the universe, a step that opens the door to deeper and more accurate truths about our extraordinary home. As the evidence piled up, scientists sought new methods to verify that the KBC void was not an artifact of limited surveys but a genuinely enormous underdensity. Traditional approaches like counting galaxies and measuring their redshifts provided strong clues, but cosmology demands independent confirmation to support extraordinary claims. One particularly compelling line of evidence emerged from the study of the cosmic microwave background, CMB, the faint afterglow of the Big Bang that permeates the universe. The CMB acts as a cosmic backdrop, a nearly uniform field against which the motion of galaxies creates subtle distortions. By examining these distortions, researchers can infer how galaxies interact with large-scale structures around them. Observations detected temperature anomalies and slight shifts in the CMB pattern along directions corresponding to the edges of our local void. These features suggested the presence of a gravitational well, or rather a gravitational deficit, on the immense scale predicted by the void model. The CMB therefore became a silent messenger, whispering the existence of the vast emptiness that surrounds us. Another powerful diagnostic tool came from the kinematic Sunyaev-Zeldovich effect, which occurs when photons from the CMB interact with gas inside moving galaxy clusters. If a cluster is moving relative to the CMB due to gravitational flows influenced by surrounding structure, the interaction imparts a measurable energy shift to the photons. By mapping these shifts, astronomers can detect large-scale motions that are otherwise invisible. When multiple galaxy clusters in and around the KBC void were observed using this method, their behavior clearly indicated they were streaming away from the void's center and toward denser regions outside it. This provided a dynamic confirmation of the void's effect on cosmic motion. The fact that the void influences galaxy clusters separated by hundreds of millions of light-years indicates a deep gravitational signature, one that cannot be casually dismissed. These results reinforced what had already become increasingly difficult to ignore. The void is not just a minor peculiarity of the local universe, but a dominant structural feature shaping our cosmic environment. Additional evidence arrived through refinements in redshift-independent distance measurements. Methods such as observing Type Oya supernova and using the Tully-Fisher relation, which compares galaxy rotation speeds with their luminosities, made it possible to determine distances without relying solely on observed recession speeds. When these distances were plotted against redshift, a consistent pattern emerged. Galaxies in our region appeared to be farther away than expected for their redshift, reflecting faster than average expansion. The deviation grew more pronounced the closer one examined the interior of the void, confirming it as the source of the anomaly. The consistency across these different techniques established the void as a tangible reality, not a statistical trick. It also highlighted a profound problem. Cosmological models calibrated on the assumption of homogeneity would inevitably misrepresent conditions inside such an extreme environment. Cosmologists therefore face a fork in the road. They must either acknowledge the void's role in shaping our measurements, or modify theoretical frameworks to account for the discrepancy. Many scientists now accept that the void represents a necessary correction to localized observations, a factor that must be included in Hubble constant calculations and galaxy flow models. Yet some remain hesitant because the existence of such a vast underdensity pushes the boundaries of what standard cosmic evolution predicts. The resistance stems not from a denial of data, but from a discomfort with the implications. The void implies that the statistical likelihood of our location is minimal, creating tension with the ideology that Earth and humanity are not cosmically privileged. Accepting such rarity feels like a retreat from centuries of progress moving away from human-centered cosmology. However, nature does not care about our philosophical preferences. The universe exists as it is, not as we wish it to be. The mounting observational confirmations show that the KBC void is neither illusion nor coincidence. It is an integral part of the cosmic architecture. The tools we use to observe the universe have grown precise, and their results converge on this same unsettling reality. Ironically, the very success of modern cosmology in refining observational accuracy has led us to the realization that our cosmic home may be far from average. As we peer deeper into the universe, measuring the relic patterns of the Big Bang and tracing the motion of faraway clusters, we also learn more about the environment from which we look. Our vantage point, once assumed inconsequential, now reveals itself as a defining variable. The void's gravitational signature serves as both a complication and a guide. It complicates interpretation but guides us toward a more complete picture of structure formation and cosmic evolution. The KBC void highlights the importance of recognizing that even the universe's most seemingly uniform features hide subtle variations that shape the trajectories of galaxies, the behavior of light, and the conclusions we draw about the grand story of existence. This recognition represents a shift in cosmology, from viewing variance as a nuisance to seeing it as essential in understanding how the universe truly works. In its silence, the void challenges the simplicity of models that once seemed unassailable, calling us to refine our theories in order to account for the extraordinary emptiness that has unknowingly cradled our observations for decades. The cosmos has delivered us a message through every wavelength we measure. Our home is a strange one, and acknowledging that truth is the first step towards solving some of the deepest mysteries yet confronting modern science. The realization that we reside within an enormous underdensity has consequences that ripple through nearly every branch of cosmology. But perhaps the most pressing of these consequences is its possible role in the Hubble tension. This tension refers to the persistent discrepancy between two different measurements of the universe's expansion rate. When cosmologists use the cosmic microwave background, essentially measuring conditions of the early universe, they calculate a lower Hubble constant. Yet when researchers measure the expansion locally using supernovae, Cepheid variables, and nearby galaxies, the value comes out significantly higher. For years, this inconsistency has troubled cosmologists because both sides of the measurement are made with extraordinary precision. If both methods are correct, and all signs suggest they are, then standard cosmology is missing something fundamental. This is where the KBC void enters the discussion. The void provides a natural explanation. Because our region of space contains much less matter than the cosmic average, less gravity is available here to slow expansion. As a result, galaxies move apart faster locally, inflating the Hubble constant measured from our vantage point. Meanwhile, the value extrapolated from the early universe remains unaffected by our atypical surroundings. This explanation has gained traction because it aligns perfectly with observed peculiar velocities and galaxy distributions. It does not require exotic new particles or modifications of general relativity, only the acceptance that we live in an unusual neighborhood. Still, many researchers hesitate to endorse the void hypothesis as the leading solution to the Hubble tension. Their reluctance stems from the principle of cosmic mediocrity, the assumption that our location should not be special. The void forces them to confront the uncomfortable prospect that we occupy a statistically rare environment. But rarity doesn't equal impossibility. Something in the universe must be rare. Statistical outliers must exist somewhere, and our existence in one of them is not a violation of physics, but merely a challenge to a philosophical assumption. The void's implications extend beyond the Hubble tension into deeper questions about the evolution of cosmic structure. Standard models suggest that density fluctuations in the early universe were small, and that large-scale uniformity should dominate at expansive distances. So how did such an immense region of emptiness arise? Some theorists propose that during inflation, the rapid expansion moments after the Big Bang rare fluctuations stretched into massive features still visible today. Those fluctuations could have left behind areas where matter never sufficiently accumulated, producing voids of extraordinary size. In this view, the KBC void is a fossil of the universe's earliest moments, a surviving imprint of primordial randomness. If true, studying its properties might reveal clues about the mechanics of inflation and the distribution of dark matter. Others suggest that cosmic variance, the unavoidable diversity of conditions across the universe, may be wider than previously believed. Perhaps vast voids are not anomalies but expected features in a cosmos built by chaos and gravity. Our presence in such a void might then reflect nothing more meaningful than being part of the universe's natural diversity. However, not all agree this explanation is sufficient. Some cosmologists argue that if voids of this scale were common, we would already have detected others. The cosmic web we observe does include many emptier regions, but nothing else quite as deep and extensive as what surrounds the Milky Way. The singularity of the KBC void continues to be one of the strongest arguments that something unusual is occupying our cosmic backyard. Regardless of interpretation, the void forces a recalibration of how we model and measure the universe. It warns that universal properties cannot be accurately determined by assuming our local environment is representative. It demands that we incorporate environmental corrections into our calculations, and it encourages new technologies and surveys designed specifically to study the influence of large-scale structure on fundamental cosmological parameters. Future telescopes and missions, such as the Euclid spacecraft and the Vera Rubin Observatory, will map galaxy distributions and cosmic flows with unprecedented accuracy. Their data will either confirm the void's role in shaping local expansion or reveal more complex interactions at play. If the void is as responsible for the Hubble tension as some suspect, its recognition may mark a turning point in cosmology, comparable to earlier revelations that displaced humanity from the imagined centers of significance. First, we learned Earth was not the centre of the solar system. Then we learned the Sun was not the centre of the galaxy, and the Milky Way not the centre of the universe. Now we may have to accept that our local region is not average but exceptionally empty. And ironically, that emptiness might be what helps us detect and understand the larger cosmos more clearly. Living in a void could be viewed not as a cosmic curse but as a scientific gift, providing us with a unique vantage to observe expansion and motion without the chaotic interference of dense environments. It is a paradox. Being surrounded by nothing has taught us more about everything. The void's influence stretches far beyond philosophical discomfort. It is a key that may unlock one of the biggest puzzles in modern science. Whether it solves the Hubble tension completely or only partly, the void has already reshaped our assumptions. It forces cosmologists to confront the profound truth that the universe is stranger, more varied, and more uneven than we once believed, and that our place within it is far from ordinary. The strange environment in which we reside has sparked more than scientific debates. It has spurred philosophical reflections on our cosmic significance. Throughout history, the greatest shifts in our understanding of the universe have occurred when we recognize that we are not in a privileged location. The Copernican revolution displaced Earth from the center of the solar system, and later discoveries removed our galaxy from any special position within the broader cosmos. These revelations shaped modern cosmology, enforcing a principle of non-specialness that became foundational. Wherever we are, the universe should look the same on large enough scales. The KBC void, however, challenges that principle directly. It does not place us at a metaphysical center, but it does suggest a highly uncommon placement, a statistical oddity that feels uncomfortably close to special treatment by the universe. This idea is unsettling, not because it implies intentional design, but because it forces us to confront the possibility that cosmic uniformity may have limits we fail to notice. If our point of observation is profoundly atypical, then we must accept that certain measurements we considered universal truths may instead be local quirks. This tension raises a deeper question. How much of our cosmological understanding is shaped by where we happen to stand? Our entire interpretation of the universe relies on the light that reaches our telescopes, and if that light has been filtered by an unusual environment, then some of our fundamental beliefs may need revision. The void teaches us that perspective matters, not just in human experience, but in cosmic inquiry. The philosophical discomfort intensifies when we consider that our rare location might be linked to our existence as observers. Some speculate that intelligent life may be more likely to arise in regions like ours, where gravitational disruption is minimal and extreme environments are kept at bay. Dense galaxy clusters, while rich in matter, are chaotic realms where gravitational interactions can tear planets apart or destabilize atmospheres. In contrast, our calmer corner of the universe allows solar systems to form without severe interference. This idea, sometimes framed through anthropic reasoning, suggests that our unusual position may not be random at all. Instead, it may reflect a subtle selection bias. We can only exist in places where existence is possible. If intelligent observers are more likely to emerge and survive in underdense regions, then perhaps the void is not as unlikely as statistics imply. But this argument walks a delicate line. It risks justifying every cosmic coincidence by appealing to necessity rather than seeking scientific explanation. Most cosmologists prefer not to rely on anthropic logic unless every other option has failed. Nonetheless, the possibility lingers in academic conversations. Maybe we are not improbable residents of a bizarre location, but typical life forms situated in the kind of environment that allows observation. Such reasoning does not eliminate the strangeness of the void, but it reframes the narrative. Instead of asking why the universe placed us in an unrepresentative location, one might ask how such locations influence the emergence of beings capable of questioning their existence. Meanwhile, the cultural implications of the void continue to grow. For many outside the scientific community, the discovery that our galaxy sits inside a massive desert of nothingness evokes existential awe. It reminds us that our cosmic home is more fragile and peculiar than once believed. The void also challenges the human desire for centrality and significance. Even in emptiness, we find ourselves confronting a new kind of cosmic humility, not that we are central, but that our loneliness is profound. In storytelling and imagination, voids often symbolize isolation. Now that symbolism stretches into the scientific realm, we live in a place where galaxies are fewer and distant, where the fabric of space stretches faster than average, where gravity is too weak to bind matter into bustling clusters. And yet, within this emptiness, life has taken root on a small world orbiting a modest star, an improbable oasis in a vast desert. The KBC void therefore becomes a reminder of how rare and precious our existence might be. Even if the void's role in the Hubble tension and cosmic structure continues to spark technical discussions, its human significance is equally powerful. It reveals a universe where extraordinary emptiness and extraordinary complexity coexist. It challenges scientists to adopt broader perspectives while still respecting empirical rigor. And it encourages us to reconsider our assumptions, not just about matter distribution, but about the very way we assign meaning to our place in reality. Ultimately, acknowledging the void pushes us toward a deeper appreciation of the universe's diversity. It suggests that cosmic history is not a story of uniform simplicity, but a tale of extremes, dense clusters, flourishing beside immense expanses of nothing. Our home lies not in the middle of everything, but in the lack of everything, and from that lack arises a new sense of wonder. The more we learn about the KBC void, the more it reshapes both scientific theory and human perspective. It forces us to ask whether we might have overlooked other anomalies simply because we never expected them to exist. It urges us to look beyond the boundaries of our philosophical comfort zone, and most importantly, it invites us to embrace the possibility that the universe, despite centuries of careful investigation, still holds surprises capable of overturning even its most sacred assumptions. If living inside a void has taught us anything, it is that reality refuses to conform to human expectations. The emptiness surrounding us is not a flaw or a mistake, it is a fundamental part of the cosmic design, and perhaps one of the most revealing. Understanding the KBC void requires not only exploring its physical characteristics, but also recognizing how its presence transforms the grand narrative of cosmic structure. The universe is often described using the metaphor of a cosmic web, a sprawling network in which galaxies are threaded along filaments, like pearls on invisible strings. These filaments intersect at vast galaxy clusters, cosmic cities buzzing with matter, and between them lie expansive voids, the dark and silent suburbs of the universe. For many years, astronomers believed that this large-scale architecture became roughly uniform beyond a certain distance. But the KBC void has shattered that assumption, revealing that even on scales of hundreds of millions of light-years, the cosmos still displays dramatic variations. In our corner of the universe, emptiness dominates the landscape. Instead of a dense intersection of cosmic filaments, we exist where those threads stretch thin and drift apart. The galaxies around us are fewer in number, spaced farther apart and tied to weaker gravitational currents than their counterparts in the more bustling regions of the cosmic web. To imagine our position, picture a massive three-dimensional foam structure where bubbles of emptiness are framed by walls of clustered galaxies. Most galaxies lie on those walls, but we find ourselves drifting nearer to the center of a bubble far from the vibrant intersections where new stars are born in drama and chaos. This unique placement has shaped our local universe in many subtle ways. The local group, the small community of galaxies that includes the Milky Way and Andromeda, evolved in relative isolation, spared from disruptive gravitational interactions that are common in denser environments. Had we been located in a massive cluster, the Milky Way might not have developed the calm, stable conditions needed for life to flourish over billions of years. Rapid galaxy collisions, tidal forces, and intense radiation often dominate such regions, creating unstable habitats for planetary systems. Our existence may therefore be partly contingent on the cosmic desert surrounding us. But while our position may support habitability, it also creates an observational trap. From inside this void, the universe seems to expand faster than the average, giving the illusion that something unusual is accelerating galaxies apart. As a result, researchers once inferred that dark energy, whatever its true nature, might be stronger or more dominant than standard models predicted. Only later did they realize that part of this effect could be attributed to the underdensity of our environment. This recognition forces cosmologists to re-evaluate many long-standing assumptions. Light from distant galaxies travels through regions of varying density, and its journey is influenced by gravitational potentials it encounters along the way. If we fail to account for these large-scale variations, then our interpretations of cosmic age, matter content, and expansion history may be subtly skewed. Scientists now use sophisticated simulations to better understand how the void interacts with surrounding structures. These simulations reveal that voids can grow over time as mass is continually pulled toward denser filaments. In this sense, voids are not static emptiness, but evolving entities' cosmic wounds that widen as the universe ages. The KBC void appears to follow this evolutionary behavior, expanding gradually while the galaxies within it drift ever farther apart. Its boundaries are marked by flowing rivers of matter, migrating toward distant superclusters like Shapley and Hercules. These flow patterns create a dynamic living structure, one that reveals the complex tug-of-war between cosmic expansion and gravity. The void is also a reminder that gravity does not act uniformly across the universe. Where matter is abundant, gravity slows the stretching of space. Where matter is scarce, expansion races ahead unimpeded. Our observatories, tuned to interpret light from billions of years ago, must now navigate this irregular gravitational landscape. Ignoring the void is no longer an option, not if we want our models to reflect reality. Despite its emptiness, the void contains hidden narratives. Faint dwarf galaxies, lone clusters, and gas clouds drift through it like nomads crossing a barren expanse. These isolated structures offer unique laboratories for studying dark matter and the evolution of galaxies in low-density environments. They behave differently than their counterparts in crowded clusters, often showing slower growth, less star formation, and reduced chemical complexity. In a sense, they evolve like small civilizations far from trade routes, quiet, slow, and self-contained. Meanwhile, the edges of the void remain more active. There, the density gradient creates gravitational pressure, as if the universe were pushing matter inward from the desert's border into richer lands beyond. Understanding this gradient is key to interpreting both local and large-distance measurements. It helps researchers correct for the distortion created by our position when mapping the cosmological terrain. Through this lens, one might view the KBC void not as an anomaly, but as a pivotal feature offering insight into how the universe distributes matter. It reminds us that emptiness is as important a player in cosmic evolution as presence. Gravity is sculpted by absence as much as by mass, and the structure of the universe is shaped equally by the places where matter never gathered. The KBC void is therefore not simply emptiness, it is a vast, influential force, guiding galaxies, shaping expansion, and challenging our assumptions about cosmic normalcy. As we continue to explore this desert of space, we uncover not a flaw in the universe, but a key to understanding its true complexity. The void expands our imagination and forces us to accept that the cosmic web is more fractal, more asymmetric, and more astonishing than the tidy formulas once suggested. The existence of the KBC void highlights a delicate balance between what the universe appears to be from our vantage point, and what it truly is on a universal scale. To many cosmologists, the void represents a warning. Never assume that the universe seen from one location expresses the full truth. Observations taken from within a giant bubble of underdensity are inevitably biased, and this bias has influenced some of the most fundamental parameters in cosmology. Consider how astronomers determine distance. They rely on standard candles like Type Ia supernovae stellar explosions so uniformly bright that their true luminosity is well understood. By comparing how bright they appear to how bright they should be, cosmologists estimate their distance. But if the region between us and those supernovae expands faster because of our void environment, then they will appear farther away than they truly are. That miscalculation directly affects the inferred rate at which the universe is expanding, pushing the local measurement of the Hubble constant upward. Meanwhile, measurements coming from the early universe tell a different story. The cosmic microwave background encodes the expansion rate billions of years ago, long before the void's influence could distort the data. The discrepancy between these two measurements becomes easier to understand once the void is accounted for. Both are correct, but pertain to different environments. In a sense, the void acts like a cosmic lens that stretches our view, making the universe seem like it's rushing apart with undue haste. The underdense surroundings amplify redshifts and distort the relationship between distance and recession velocity. That distortion doesn't invalidate the expansion, it simply means our neighbourhood accelerates slightly more than average. Addressing this challenge demands more than simply inserting a correction factor. It requires redefining the scale at which we consider the cosmos to be homogeneous. The old belief that uniformity begins just a few 100 million light-years away no longer holds. The KBC void extends much farther than that threshold, forcing scientists to reconsider the boundaries of cosmic consistency. The void also raises questions about the concept of cosmic variance. For decades, researchers assumed that large-scale variations in density even out across the sky. But now they must accept the possibility that such variations can be so significant that they disrupt what we call the cosmic average. The implication is profound. The universe might not be as statistically smooth as theory once demanded. If such giant anomalies exist, then cosmological models must embrace the messy truth that rare environments do happen, and we may be experiencing one firsthand. Yet, it is important to understand that this does not break cosmology. Rather, it enriches it. The universe becomes a more dynamic, varied landscape where matter doesn't settle into perfect symmetry, but forms sprawling deserts and bustling metropolises of galaxies. The void underscores the importance of recognizing that our observations are not made from a neutral laboratory, but from a specific address, a cosmic coordinate that shapes everything we perceive. This realization has driven new methodologies. Scientists have developed cosmological simulations designed to include enormous voids and measure their effects on observable quantities. They study how light travels through such underdense regions and determine how typical measurements, brightness, redshift, gravitational lensing change depending on where in the cosmic web an observer is located. These simulations reveal that observers embedded in large voids consistently measure higher Hubble constants than those in denser environments. This is precisely what we see in reality. Instead of insisting that one measurement is flawed, cosmologists are beginning to accept that context matters. The universe does not assign the same conditions to all observers, and so their observations naturally differ. A crucial step forward came when researchers began mapping galaxy motions in 3 dimensions rather than relying solely on redshift. These velocity field reconstructions revealed coherent outflows from our region, exactly as expected if the void dominates local structure. The depth of the underdensity, combined with its spherical geometry, creates a push outward in every direction. This spherical symmetry is a compelling indicator that the void is not a minor feature, but a dominating force that shapes the entire observed horizon. While the universe remains governed by universal laws, those laws manifest differently in varying environments. From dense cluster cores to sprawling voids, cosmic evolution follows the same rules but yields different outcomes depending on the initial conditions. The KBC void illustrates this beautifully, a structure where the subtleties of gravity and expansion reveal themselves with striking clarity. The next step for cosmology is to refine our tools so that they account for environmental influence by default. Distance measurements must be corrected for local expansion effects, and surveys must reach well beyond the void's boundaries to gather truly representative data. As models improve, the Hubble tension may no longer appear as a disagreement, but as a natural consequence of viewing the universe from a peculiar seat. Instead of rewriting the physics of dark energy or inventing new cosmic components, we may simply rewrite our assumptions about what it means to take a measurement in the universe. The KBC void teaches us that the cosmos is not designed to make things easy for observers. It reminds us that our knowledge is situated anchored to a location that could never be perfectly typical. And far from diminishing the power of cosmology, this understanding strengthens it, revealing that even emptiness can be rich with lessons about the nature and behavior of the universe on its grandest scales. To grapple fully with the implications of the KBC void, we must look closely at how galaxies behave when they reside in such a vast region of low density. In the heart of the void, the gravitational environment is noticeably different from that in denser sectors of the universe. Matter is scarce and scattered, resulting in weaker gravitational pulls and a calmer cosmic neighborhood. The growth of galaxy clusters slows dramatically, and the formation of new stars becomes less frequent as gas becomes diffuse and harder to compress. Studies of void galaxies show they tend to be smaller, contain fewer heavy elements, and evolve more slowly than galaxies in dense clusters. This makes them ideal laboratories for testing theories about dark matter and galaxy evolution, because the influences of violent gravitational interactions are minimal. If dense clusters are bustling cities shaped by constant interactions, void galaxies resemble quiet countryside settlements, where changes unfold gradually. This serenity, though unusual, has allowed our galaxy to live a stable life. In a more tumultuous region, such as a rich galaxy cluster, the Milky Way might have collided with neighbouring galaxies long before life emerged on Earth. Violent mergers, intense radiation fields, and turbulent tidal forces fill such environments. Here in our quiet enclave, the Milky Way and Andromeda drift toward each other slowly, set for a gentle union billions of years in the future. Cosmic voids therefore offer a protective cradle for planetary systems, allowing fragile conditions like Earth's biosphere to persist. The calm interior of the void stands in sharp contrast to its periphery, where conditions grow increasingly interactive. Near the borders of the void, matter density rises and gravitational attraction strengthens. Galaxies in this region experience more substantial flows, drawn toward massive structures that define the cosmic web. These flows shape peculiar velocities and create patterns of motion that reveal the gravitational push and pull of the void on the surrounding universe. It is here that the influence of the void becomes unmistakably clear. Galaxies do not simply participate in the uniform expansion of space. They are propelled outward by the weakness of gravity inside the void and drawn inward by dense regions outside it. This coordinated movement confirms the existence of a major underdensity with us near its centre. The consistency of these flows across enormous distances eliminates the possibility of coincidence. We observe a coherent push that aligns perfectly with expectations from the void model. The relationship between voids and dense structures can be imagined as a type of cosmic respiration. The universe breathes as matter collapses into clusters, while expansion stretches the empty spaces wider. The KBC void is one of the largest chambers in this cosmic lung, expanding gradually as surrounding gravity pulls matter toward the filaments. This dynamic behavior turns the void into a kind of gravitational engine that shapes cosmic flows on scales larger than entire superclusters. Yet this engine does not run wildly. It follows laws that, while complex, remain consistent with standard cosmology when environmental variation is properly considered. That point is crucial because it reveals another truth. The KBC void does not represent a breakdown of our models, but an extension of them. It demonstrates that the universe is capable of producing rare structures within the boundaries of known physics. The only adjustment required is that we broaden our expectations for how extreme those structures can be. The presence of such a remarkable void also forces us to revisit our assumptions about sampling in science. If our cosmic observations are taken primarily from a single, unusual environment, then our conclusions cannot be assumed to reflect universal norms without careful correction. This concept echoes similar realizations in other fields. A biologist who studies only desert life would misunderstand Earth's ecosystems. A geologist who examines only volcanic islands would misjudge the nature of mountains. Likewise, astronomers must recognize that our cosmic address shapes the data we gather. Only by comparing observations from many different environments, using distant galaxies, gravitational wave signals, and deep field surveys, can we confirm which aspects of our universe are truly universal. As technology advances, we will peer farther beyond the void and observe regions untouched by its distortions. Those observations may act as a calibration tool, allowing us to adjust local measurements and reconcile them with global cosmic parameters. This approach will likely reduce the apparent Hubble tension, revealing that the discrepancy comes not from flawed physics, but from our position in a large-scale structural anomaly. Understanding the void therefore empowers cosmologists rather than undermining them. It offers a key to solving long-standing puzzles that once seemed to demand radical new theories. It also forces us to appreciate the complexity of the cosmic web in a new way. The universe is not a perfect lattice, but a rich landscape of diversity-dense hubs and empty expanses coexisting across billions of light-years. Recognizing that we live in one such expanse reshapes our interpretation of cosmic evolution, while deepening our appreciation of the delicate conditions that make our existence possible. Living in a void has given us clarity. It has provided a peaceful corner of the universe where life can emerge, where skies remain dark enough to reveal distant galaxies, and where astronomers can observe cosmic expansion with remarkable precision. The consequences of our environment are profound, influencing both our survival and our understanding of existence. The KBC void, far from being a scientific inconvenience, might actually be the reason we are here to study it in the first place. As cosmologists delved deeper into the nature of the KBC void, they realized its existence offered an opportunity to test some of the universe's most intriguing unanswered questions. Among these is the mysterious force known as dark energy, the invisible driver behind cosmic acceleration. Dark energy is inferred rather than observed directly, detected only through its influence on the expansion of space. When scientists noticed that galaxies were moving apart faster than expected, they proposed that some form of repulsive energy permeates the cosmos. But if our region of the universe is underdense, then the expansion we witness is partly due to the lack of gravitational slowdown, not solely due to dark energy. This raises a subtle but important complication. How much of the acceleration we observe is universal, and how much is a local exaggeration created by the void? The answer to that question could refine or even redefine the role of dark energy in cosmology. Some researchers suggest that the void acts like a natural amplifier of expansion, making dark energy seem more dominant here than it actually is elsewhere. If true, then the standard models estimating the strength of dark energy may need adjustment. Others argue that the void provides a real-world test case for how dark energy behaves in environments with extremely low matter density. Perhaps dark energy interacts differently with empty regions than with crowded ones. While this idea remains speculative, the void forces cosmologists to consider such possibilities more seriously. The presence of the KBC void may also influence interpretations of the curvature of space. For many years, evidence suggested the universe is remarkably flat on large scales, meaning space does not bend significantly upward or downward. But localized structures can create the illusion of curvature when measurements are taken from within them. A void causes space to expand faster inside than outside, introducing a false curvature into observational data. Some discrepancies in curvature estimates may therefore be artifacts of our location within this vast bubble. In this case, the void becomes more than a local feature. It becomes a lens that bends not light, but understanding. To account for these distortions, cosmologists must carefully distinguish between global measurements, those reflecting the universe at large, and local ones influenced by our immediate surroundings. This dual-layered approach is critical as we attempt to reconcile observations across different scales and epochs of cosmic history. The void also affects how we interpret the clustering of galaxies. In denser regions, gravity brings galaxies together more readily, leading to rich superclusters and complex filament networks. If much of our surveying occurs from within a void, the frequency and distribution of such structures may appear skewed. We may underestimate how common tightly clustered regions are simply because we live in a relatively isolated one. This realization emphasizes a recurring theme. Our cosmic vantage point, once assumed to be unremarkable, is deeply influential. The void has even sparked new lines of thought concerning cosmic symmetry. While isotropy, the idea that the universe looks the same in every direction, has held firm in most observations, the presence of a large asymmetry in density challenges the assumption of uniformity across vast distances. Though the void does not imply the universe has a center or an edge, it reveals that large-scale variations can be more extreme than theory once allowed. To some, this suggests that the Copernican principle must evolve. It is not enough to claim we are not in the center of all things. We must also acknowledge that some locations are inherently different, and we happen to occupy one such location. This does not return humanity to a privileged cosmic pedestal, but requires humility of a new kind, a recognition that the universe is filled with diverse environments we have yet to explore. Ultimately, the KBC void demonstrates that cosmology is not only about measuring distant galaxies or decoding ancient light. It is about understanding our relationship to everything we observe. Our tools and methods must adapt to account for the influence of local structure. As future measurements become more precise, we will refine our cosmological models to reflect a universe that is beautifully irregular. Giant voids like ours serve as natural laboratories, testing the limits of current theories and creating opportunities for new discoveries. They remind us that anomalies are not obstacles, they are invitations to deepen our understanding. The more attention we give to the void surrounding us, the more we uncover about the forces shaping the cosmos. and as difficult as its implications may be for long-held assumptions, the void reveals the universe as it truly is. Not an idealized equal expanse, but a living structure shaped by both presence and absence, gravity and expansion, matter and emptiness. In embracing this truth, cosmology matures, becoming a science not only of averages but of environments, one capable of seeing beauty in both the crowded richness of galaxies and the silent expanses in between. The KBC void stands as a reminder that even emptiness can hold extraordinary meaning when viewed through the eyes of discovery. One of the most compelling aspects of the KBC void is how it intersects with the hidden framework of the universe dark matter. Dark matter, although invisible, shapes the cosmos more decisively than anything we can see. It sculpts the filaments of the cosmic web, anchors galaxy clusters, and dictates the gravitational landscape on grand scales. Without dark matter, galaxies would not hold together. They would spin apart into scattered stars. When astronomers explore void regions, they discover not only an absence of ordinary matter, but also a deficit of dark matter. This shortage deepens the underdensity and explains why gravitational attraction is so minimal inside the void. It also provides a window into the nature of dark matter itself. Because void environments are free from the chaotic gravitational interactions found in crowded clusters, they reveal how dark matter behaves in near isolation. Some simulations suggest that dark matter distribution in voids becomes smoother, lacking the clumps that seed galaxy formation. Others show faint strands of dark matter stretching across emptiness like barely visible threads. These subtle features might help solve mysteries about dark matter's interaction, or lack thereof, with itself and with normal matter. While dense regions highlight the strength of dark matter's gravitational pull, voids emphasize its vulnerability to evaporation and dispersal. The KBC void therefore functions as a natural experiment, exposing how dark matter responds when gravitational pressure is relaxed. Furthermore, the void may help unravel another cosmic riddle: the apparent mismatch between observed baryonic matter and predictions from early universe models. It has long been recognized that we observe only a fraction of the matter that should exist. Some of this missing matter is believed to reside in the warm-hot intergalactic medium gas stretched between galaxies along filaments. But within a void, where filaments thin and gas cools, this material becomes even harder to detect. Studying the void may thus reveal where some of the universe's missing matter is hiding, helping close the gap between theory and observation. The behavior of galaxies in the void also highlights the connection between dark matter and star formation. In richer environments, mergers and tidal forces compress gas and trigger new generations of stars. In voids, those processes occur rarely. Dark matter halos struggle to gather enough baryonic material to ignite star factories. As a result, void galaxies tend to be smaller, fainter, and more primitive snapshots of a slower evolutionary path. This provides a unique parallel to the early universe, where galaxies were just beginning to form. Studying void galaxies is like watching cosmic history run in slow motion. Their isolation preserves conditions similar to those present shortly after the Big Bang, offering insights into galaxy growth free from the complexities of dense environments. The KBC void also pushes cosmologists to think more deeply about gravitational dynamics on large scales. Although dark matter dominates structure formation, gravity weakens dramatically across immense voids. In these regions, expansion gains the upper hand, gradually pulling galaxies apart and widening the empty spaces. This interplay between gravity and expansion may hold clues to understanding dark energy, which accelerates the stretching of space everywhere. Some theorists suggest that dark energy and void growth are two expressions of a single underlying phenomenon. If voids expand faster than average, perhaps they amplify the effects of dark energy locally. This could help explain variations in expansion rate and potentially reduce reliance on new physics. However, not all researchers embrace this interpretation. Some argue that dark energy remains uniform and that void expansion merely highlights the natural consequences of gravitational imbalance. Still, the interaction between the void and dark energy remains an active area of inquiry, one capable of reshaping foundational cosmological equations. The void also raises questions about cosmic connectivity. If large voids inhibit gravitational communication between regions, then parts of the universe may be evolving somewhat independently. This suggests the possibility that the cosmos is less synchronized than previously thought, Instead of behaving as a smoothly connected whole, it may unfold in pockets, each influenced by its own density environment. The KBC void could be one such pocket or region whose timeline and structural evolution differ subtly from the cosmic average. Understanding this divergence is crucial for interpreting data from deep surveys that span billions of light years. Finally, the void serves as a reminder of how incomplete our maps of the universe still are. Despite tremendous advancements in observational astronomy, vast expanses remain barely charted. Some of the matter we cannot detect may be spread thin across voids, waiting for future instruments to reveal its presence. And while darkness dominates these regions, they are not devoid of information. On the contrary, studying emptiness reveals the unseen framework that supports everything else. The KBC void, once overlooked as mere absence, is now recognized as a key piece in the grand puzzle of the cosmos. It embodies the delicate balance between gravity and expansion, the dance of dark matter and galaxies, the tension between observation and theory. In facing the void, cosmology grows more mature, learning that the universe's secrets are not found only where matter gathers, but also where it refuses to appear. The recognition that we inhabit a massive underdensity did not emerge overnight. It was the result of decades of gradual discovery as astronomers refined their tools and broadened their surveys. Early cosmological studies were limited by technology and perspective. Much of the universe was hidden behind the dense plane of our own Milky Way, and galaxies farther away than a few million light-years were too faint to detect reliably. As telescopes improved, astronomers began to see the grand architecture of the universe, a tapestry of clusters and filaments separated by expanses of emptiness. Yet even then, it was difficult to determine whether our local region was truly unusual or simply part of a pattern too large to perceive from within. Some early galaxy surveys noted curious gaps in certain directions, but these findings were often dismissed as observational artifacts, limitations of instruments, dust obstruction, or incomplete sky coverage. The idea that the Milky Way could reside in a uniquely empty region conflicted with the widely accepted belief in uniformity on large scales. But the inconsistency refused to disappear. As redshift mapping advanced, researchers began to measure not just positions of galaxies but their motions, unveiling deviations that hinted at something enormous, a gravitational imbalance stretching across the surrounding cosmos. These peculiar velocities did not match what would be expected if the local universe were average. Instead, they suggested a powerful outward acceleration, centered eerily close to our galactic coordinates. Yet even then, many scientists hesitated to interpret the anomaly as evidence of a gargantuan void. The stakes were high. Acknowledging such a structure would force major revisions to foundational assumptions. It wasn't until the work of Keenan, Barger and Cowie in the early 2010s brought together multiple datasets, galaxy counts, density estimates, and distance comparisons that the pieces finally aligned into a cohesive picture. Their analysis demonstrated that the matter density in our region was significantly lower than the cosmic mean over a vast span of hundreds of millions of light-years. Later refinements expanded the estimated size to nearly 1 billion light-years, solidifying the existence of what is now called the KBC void. Subsequent evidence only strengthened the case. Gravitational lensing surveys showed weaker curvature of light than expected in our region, confirming the absence of mass. Large-scale velocity field reconstructions revealed systematic flows outward from the void's center, as if the surrounding universe was subtly repelled by the lack of gravitational anchor here. Meanwhile, the kinematic Sunyaev-Zeldovich effect exposed the motion of galaxy clusters responding to this imbalance. Each line of inquiry pointed to the same conclusion. The emptiness around us was not a statistical fluke, but a defining structure of the local cosmos. As more observations accumulated, the question shifted from "does the void exist?" to "how much does it distort our view of reality?" When cosmologists realized how profoundly our placement affected measurements of the Hubble constant, the void transitioned from a curiosity to a central character in one of modern astronomy's most debated controversies. The Hubble tension, once thought to be a technical discrepancy, may instead reflect the cosmic truth that expansion appears different depending on one's environment. Living in a void accelerates the measured recession of galaxies, making the universe appear younger and more dynamic locally than when viewed from denser regions. Not all scientists accepted this explanation immediately. Some argued that survey boundaries and sampling limitations might be misleading researchers into inferring a void larger than what truly exists. Others worried that embracing such a rare structure undermined the philosophical backbone of cosmology. Yet resistance gradually weakened as better data poured in. The Sloan Digital Sky Survey, TUMAS, and more recently the DESI and Euclid missions have all contributed to mapping the deep structure with increasing precision. Today, a growing consensus acknowledges the KBC void as a genuine and massive underdensity, though debate continues over exactly how much it alters inferred cosmological parameters. What is certain is that the void has become a catalyst for scientific progress. It has forced researchers to design more sophisticated models capable of capturing environmental variation. It has driven the development of new analysis techniques that extract velocity flows, reconstruct density fields, and isolate the impact of local structure. It has inspired fresh theories about the formation of voids and their relationship to cosmic inflation. The story of the KBC void illustrates how science evolves when unexpected evidence compels us to expand our thinking. It shows that the universe can defy expectations even after centuries of cosmic exploration. We once believed the Earth was central, then the Sun, then the galaxy. Now, we must confront the fact that our location may be central only to a vast region of nothingness. But instead of shrinking our significance, this discovery enhances the mystery of why we are here and why our corner of the universe looks the way it does. The journey from denial to acceptance of the void underscores a defining feature of scientific progress. When faced with new truths, the universe challenges us to adapt, not resist. The KBC void is a testament to that challenge, a reminder that the cosmos remains vastly more complex and surprising than the neat models we construct to comprehend it. While the KBC void has already reshaped key elements of cosmology, it continues to challenge the observational strategies used to interpret the universe. Much of what we know is filtered through assumptions built into the instruments and analytical frameworks astronomers rely on. Distance ladders, redshift mapping, and velocity reconstructions all depend on the premise that the local environment does not dramatically differ from the cosmic average. The discovery that we occupy a region with unusually low matter density compels a thorough re-examination of these methodologies. For instance, the standard approach to determining expansion relies heavily on redshift-based distance measurements. Redshift is treated as a clean proxy for cosmic expansion, assuming peculiar velocities are minor corrections. But inside a void, peculiar velocities are not merely noise, they are fundamental to interpreting the data correctly. When galaxies are being gravitationally pushed outward due to underdensity, their additional velocity falsely inflates the inferred expansion rate. If this effect is not carefully modelled, cosmologists run the risk of misinterpreting core properties of the universe, including its age and the strength of dark energy. The implications extend even to the cosmic distance ladder's foundational rungs. Cepheid variables and Type Ia supernovae are often used to calibrate luminosity-based distance indicators, but their distribution is likewise shaped by the cosmic web. Underlying assumptions about their intrinsic brightness may be slightly altered by environmental factors such as metallicity, star formation history, and gravitational context, all of which differ between voids and dense clusters. It becomes clear that treating the local universe as representative is no longer justifiable. Even low redshift measurements, once thought to be the most reliable, must now be corrected for the void's distortive influence. Moreover, gravitational lensing surveys, once heralded as unbiased probes of mass distribution, are also susceptible to environmental distortion. In a void, the lack of mass leads to significantly reduced lensing signals. If used without adjustments, lensing-based mass estimates could misleadingly suggest that dark matter is more scarce than it truly is across the universe. Therefore, cosmologists must take great pains to distinguish between local anomalies and universal truths. This does not only affect mapping of mass, but also the interpretation of gravitational wave signals. Events like neutron star mergers are increasingly used as standard sirens for cosmological distance measurement. But the propagation of gravitational waves, just like light, is shaped by the large-scale environment they traverse. Passing through an enormous underdensity alters their amplitude and timing ever so slightly, potentially skewing derived distances unless environmental corrections are applied. For these reasons, researchers are developing new frameworks that embed cosmological measurements inside detailed density models. One promising technique involves reconstructing the local gravitational field from galaxy surveys and using that model to adjust observed redshifts, effectively subtracting the void's influence to better approximate the true cosmic expansion rate. In addition, deeper surveys extending well beyond the boundaries of the void are crucial. Only by anchoring local measurements to those obtained in drastically different environments can cosmologists build accurate models that reflect the full diversity of the cosmic web. Tools like the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, and ESA's Euclid mission aim to chart billions of galaxies across wide distances, creating density maps with clarity never before achievable. These projects promise to illuminate whether the KBC void is a rare curiosity or part of a broader pattern of enormous underdensities scattered throughout the universe. Another frontier involves theoretical work, large simulations incorporating voids as central elements rather than peripheral auditors. Models are now being updated to allow for underdensities of significant size, showing how they grow and interact with neighboring filaments and attractors. These simulations test whether the void's existence aligns comfortably with LCDM, the standard cosmological model, or whether we must revise our understanding of how dark matter and dark energy sculpt structure. As unsettling as the void once seemed, it now offers an invaluable opportunity to explore physics under conditions not easily replicated in dense regions. By examining extremes, places nearly devoid of matter, we gain a fuller grasp of the universal laws governing space and time. The lesson emerging is not one of despair over flawed assumptions, but excitement for new precision. The void highlights how sensitive our interpretations are to environment, and how advances in measurement technology must be accompanied by advances in conceptual frameworks. It ensures that future cosmology becomes more nuanced, embracing complexity instead of artificially smoothing it away. In the end, the vast emptiness around us does not undermine the achievements of cosmology. It refines them. It reminds us that the universe is not a uniform classroom but a sprawling and uneven frontier. Our task is not merely to measure it, but to understand how our measurements are shaped by the unique seat from which we observe. In acknowledging the void, we transform from naive observers, assuming typicality, to sophisticated explorers aware of the context influencing every beam of light that reaches our telescopes. That evolution marks the true progress born from recognizing the KBC void, a deeper maturity in our scientific vision, and a readiness to embrace the universe not as an idealized model, but as the unpredictable and wondrous reality that surrounds us. The deeper scientists investigate the KBC void, the more they recognize that its significance extends far beyond the borders of astrophysics and touches on the philosophical foundations of how humanity perceives the cosmos. Throughout history, our understanding of the universe has often been shaped by mistaken assumptions about our place within it. For centuries, humans believed Earth stood still at the center of creation. That misconception eventually gave way to the knowledge that our planet orbits the Sun, and later to the realization that our Sun is just one star among billions in the Milky Way. We later discovered that our galaxy itself is only a humble member of a vast cosmic web with no privileged status. Yet once again, we face the paradox that our local environment may be exceptional, not because we are at the center of existence, but because we find ourselves in one of the most empty regions ever discovered. This is not a reversal of the Copernican principle, but an evolution of it. We must accept that our perspective is unavoidably shaped by our environment, and that environment is not cosmically average. This revelation raises profound questions. If the laws of physics appear different in different regions of the universe due to environmental conditions, then what does it mean to describe universal truths? Our cosmic measurements may never escape the influence of our neighborhood, unless we develop techniques capable of seeing beyond its distortions. Instead of comparing ourselves to some perfect cosmic norm, we must embrace a more dynamic framework that acknowledges diversity in cosmic environments. Recognizing this context does not diminish our understanding. It enhances it by adding depth and nuance. The void challenges the comforting simplicity of uniformity and forces us to confront a universe that is far richer and more textured than the smooth models once suggested. In practical terms, this means the future of cosmology requires cooperation between observation, theory, and advanced modelling. By synthesizing data from multiple sources, gravitational waves, deep-field galaxy surveys, supernova catalogues, and cosmic microwave background analysis, scientists hope to separate local effects from global behaviour. This multidisciplinary approach is pushing astronomy into a new era, in which the study of environment will be equally important as the study of the cosmos at large. The KBC void serves as a reminder that even enormous advancements in technology do not guarantee accurate perception unless we also evolve the conceptual frameworks that interpret the data. It is not enough to build bigger telescopes or more sensitive detectors. We must also train ourselves to recognize the limits imposed by our cosmic vantage point. Only by acknowledging that every measurement is shaped by location can cosmologists uncover the genuine global properties of space. At the same time, the existence of the void invites speculation about how cosmic structures originate and grow. Traditional theories suggest that the universe began in a nearly uniform state, with slight fluctuations in density. These primordial deviations, amplified by gravity, blossomed into the intricate cosmic web we observe today. But the presence of a void as large as the KBC raises the question of whether such fluctuations were even more dramatic than previously thought, or whether inflation, the rapid expansion of space in the early universe, produced features far more extreme than models currently predict. This has motivated fresh explorations of inflationary theory and alternative cosmological models that might allow for significant variations in density on gigaparsec scales. The void also fuels curiosity about the possibility of multiple sprawling underdensities spread across the universe. If our void is not unique, then the cosmic web could be punctuated by many such vast depressions, each influencing the expansion and structure of its surroundings. This would imply that cosmic evolution is even more sensitive to initial conditions than anticipated. The void thus plays a key role in rethinking the nature of cosmic predictability. While the large-scale structure emerges from statistical processes, the specifics like where voids appear and how large they grow may be far more dependent on randomness and historical accident. Our existence in a calm, underdense region might not be cosmically central, but it is profoundly consequential. The very conditions that make our environment unusual may also make it uniquely hospitable. Without the isolation of a void, intense cluster-driven interactions could have rendered our galaxy too unstable to nurture complex life. In a poetic sense, the void may be the quiet backdrop that allowed consciousness to awaken and contemplate the universe. That connection between cosmic structure and human existence bridges the realms of science and philosophy, inviting us to consider how intimately our fate is tied to the architecture of the cosmos. The more we learn about the KBC void, the more we realize that emptiness is not absence but influence, a silent force that shapes both the evolution of galaxies and the evolution of ideas. In this way, the void stands not as a threatening abyss but as a profound teacher. It encourages us to remain humble before the mysteries that surround us and determined to unravel them. Even in the deepest darkness, the universe provides clues that lead us toward greater understanding, reminding us that knowledge expands not only by exploring places filled with stars, but also by studying the vast enigmatic spaces where stars are few. As researchers continue to investigate the KBC void, they increasingly recognize that understanding such enormous underdensities requires a blend of theoretical insight and cutting-edge observational precision. It is not enough to observe galaxies only where they shine brightest. Cosmologists must also measure the darkness between them with equal determination. One exciting development in this pursuit is the expanding use of cosmic mapping technologies, capable of peering through enormous distances with unprecedented detail. Instruments such as the Square Kilometre Array, SKA, the James Webb Space Telescope, and the Euclid space mission promise to chart not only the galaxies that define the filaments, but also the faint structures and subtle gravitational influences that fill the voids. Detecting the faint glow of intergalactic hydrogen, the whisper of dark matter through weak lensing, and the distortions left behind by ancient cosmic events allows researchers to reconstruct the invisible skeleton of the cosmos. Through these efforts, astronomers hope to refine the boundaries of the KBC void, revealing whether it has a smooth spherical shape or a more irregular shifting geometry that connects seamlessly to neighbouring voids. The patterns they uncover may prove essential to decoding how the cosmic web evolved over billions of years. A critical area of focus is the void's interaction with major gravitational attractors outside its boundaries. Observations indicate that beyond our underdense surroundings lie some of the most massive structures nearby, such as the Shapley supercluster. Their immense gravitational pull guides galaxy flows that swirl around the edges of the void, creating large-scale motion patterns like cosmic tides. These motions allow researchers to estimate the contrast between the void's interior and the denser outskirts. If the matter deficit is too small, the effect on expansion would be negligible. But if it is deep enough, the observed acceleration within the void becomes a natural consequence of living in a region where gravity cannot effectively resist expansion. This observational dance between emptiness and gravity helps determine whether the void alone can significantly contribute to the Hubble tension, or whether dark energy must still carry most of the explanatory weight. Meanwhile, galaxy evolution within voids remains an ongoing mystery rich with clues. Observations show that void galaxies tend to be rich in gas and surprisingly efficient at forming stars relative to their small size, possibly because they are free from disruptive gravitational encounters. Their chemical compositions suggest a slower enrichment history, giving astronomers a look at how galaxies might have evolved if left largely undisturbed since early cosmic times. These isolated galaxies provide laboratories for studying dark matter halos that grow without frequent mergers, potentially offering new constraints on dark matter particle properties. By comparing void galaxy populations with those in clusters, scientists gain insights into how environmental pressure shapes the fate of cosmic structures. The void also invites experimental theorists to revisit assumptions about the universe's earliest moments. If the initial density fluctuations that seeded the cosmic web were stronger or more uneven than predicted, that might help explain how such a massive void emerged near our location. Some cosmologists speculate that inflation responsible for the universe's rapid expansion shortly after the Big Bang may have amplified certain regions more than others, producing rare features like the KBC void. If such inflationary anomalies are confirmed, they could rewrite our understanding of the earliest stages of the universe and reveal new physics operating beyond current models. Others explore whether the void might indicate the presence of exotic dark energy dynamics or even modifications to gravity itself. While these ideas remain speculative, the mere fact that they are now being considered highlights the void's power to push cosmology into fresh terrain. Importantly, progress in understanding the void fosters increasingly collaborative research efforts. Cosmologists specializing in large-scale structure join forces with particle physicists exploring dark matter, with astrophysicists studying galaxy evolution, and with philosophers questioning the nature of cosmic typicality. The void has become a crossroads, where different scientific disciplines converge because its implications reach across so many boundaries. This growing synergy encourages the development of integrated models that reflect a universe far more complex than the oversimplified templates of the past. Even as technology improves, the void reminds us that comprehension grows not only through better data, but also through more imaginative thinking. The KBC void is not merely a blank feature on the cosmic map. It is a phenomenon that teaches us how fragile our assumptions can be. It shows that the universe is comfortable producing structures that challenge statistical expectations, and that the rare does not imply the impossible. While we often look to the brightest and most crowded places to learn about cosmic laws, the void proves that silence and scarcity can be equally instructive. In a poetic sense, the space between galaxies carries its own kind of narrative, one that speaks through absence rather than abundance. The KBC void encourages us to listen closely to that story, to honor the lessons revealed by what is not there, and to continue exploring the vast uncharted territories of the cosmos, where darkness shapes the light we see. As the exploration of the KBC void continues, scientists recognize that its significance lies not only in its physical attributes, but also in what it can reveal about the unseen actors shaping cosmic evolution. Among these hidden forces, dark energy remains the most enigmatic. While dark matter provides the scaffolding on which galaxies assemble, dark energy stretches the universe apart, accelerating its expansion. Yet even now, the true nature of dark energy is unknown, whether it is a constant inherent property of space or a dynamic field that varies across time and environment. The KBC void has emerged as a natural testing ground for this mystery, because underdense regions exaggerate the effects of cosmic acceleration. When gravity is weaker due to the scarcity of matter, expansion operates with fewer restraints, allowing dark energy's influence to become more apparent. If dark energy behaves differently in emptier spaces, the void could provide the first hints of such variation. Understanding how the void expands could therefore offer powerful clues about whether dark energy is uniform or interacts with matter in ways yet to be understood. Another intriguing angle comes from studying how light and gravitational waves travel through the underdensity. As both propagate through the void, they experience fewer gravitational wells pulling on them, allowing subtle differences in speed, lensing, and trajectory compared to their path through denser cosmic areas. These slight distortions can be measured with extreme precision using modern telescopes and interferometers, creating a new class of void cosmology experiments. By comparing signals that cross the void with those that traverse more structured environments, researchers can isolate how emptiness alters fundamental cosmic measurements. Meanwhile, the KBC void also provokes deeper thinking about the completeness of our knowledge of matter itself. Although it is described as empty relative to the cosmic average, the void still contains intricate features: clouds of hydrogen gas, dark matter filaments stretched thin, lone dwarf galaxies sparkling like islands in a cosmic sea. Detecting such faint structures requires cutting-edge sensitivity because the signals are whisper-level quiet. Future observatories will likely expose a surprising richness of faint galaxies that have remained invisible until now. These faint galaxies are important because they hold information about the earliest star formation episodes in the universe. In dense regions, countless mergers obscure these early evolutionary pathways, but in voids, galaxies retain their primordial characteristics for far longer. The KBC void thus serves as an archive, a place where cosmic history is preserved rather than overwritten by constant interaction. Light from these quiet galaxies carries information about the universe's youth, allowing astronomers to reconstruct what conditions were like when galaxies began to ignite billions of years ago. Equally fascinating is the idea that voids like ours may be gateways to studying exotic physics that rarely manifests in dense environments. Some theoretical models suggest that if dark matter consists of particles capable of self-interaction, those behaviors might appear most clearly where gravitational pressure is low. Others propose that voids could amplify effects from hypothetical scalar fields influencing dark energy or gravity. Carefully observing deviations from expected behavior in the void may help confirm or refute such theories. The very existence of such an immense underdensity encourages scientists to keep refining simulations to determine how such structures naturally develop within standard cosmology. Current models show that voids grow as galaxies migrate outward along expanding boundaries into surrounding filaments. But the KBC void seems exceptionally large, raising questions about whether our cosmic neighborhood underwent unique initial conditions, or whether similarly vast voids are more common than previously recognized. To address this, astronomers compare our void with distant regions to search for patterns, whether the universe routinely forms such emptiness, or whether our location is truly unusual. If numerous giant voids exist, then cosmological theories must account for their frequency. If they are exceedingly rare, then we must examine why our region is one of the few that evolved into such emptiness. In addition to scientific investigation, the presence of the void fosters a new kind of curiosity about the cosmic landscape. It forces us to wonder what future explorers might discover as they traverse beyond our local emptiness into denser realms. Just as early navigators at sea once mapped coastlines to understand unfamiliar environments, astronomers now chart filaments and voids to comprehend the vast structure that defines the universe. The KBC void represents a frontier silent, subtle, and immense, reminding us that knowledge often expands most profoundly, not just where activity peaks, but where it nearly vanishes. And perhaps the most profound message the void offers is that emptiness itself plays an active role in shaping what exists. The cosmic landscape is not defined only by stars, planets, and galaxies, but by the vast abysses between them. It is within those abysses that expansion accelerates, matter flows, and the fate of the universe as a whole is determined. In recognizing this, the KBC void becomes more than an unusual neighborhood. It becomes a fundamental key to understanding how the universe breathes, grows, and endures across the ages. Even in silence, it speaks about origins and destinies, inviting us to listen more closely to the lessons it whispers from the darkness. As understanding of the KBC void grows, the implications spill outward into ideas about the future of cosmology and the ultimate fate of the universe. What once seemed like an obscure curiosity is now recognized as a phenomenon capable of reshaping predictions about cosmic destiny. In a universe increasingly dominated by dark energy, regions like voids may continue expanding faster than their surroundings, becoming even more isolated as time unfolds. Over billions of years, galaxies inside the void, including our Milky Way, may drift farther apart, their light becoming too faint to detect from one another. If dark energy continues to accelerate expansion indefinitely, distant galaxies will gradually slip beyond our observable horizon, disappearing into darkness as their photons can no longer reach us. The universe will not collapse into darkness because of death or destruction, but because of distance. This cosmic loneliness scenario becomes especially vivid when we consider our location in a massive void. The emptiness around us means fewer galaxies to begin with, accelerating the timeline of observational isolation. Eventually, future astronomers living in the far future of the Milky Way might have no evidence of the broader universe at all. They may believe their galaxy is the entire cosmos, just as humans once did before telescopes revealed the truth. This possibility places a philosophical weight on our current era. We are alive at a cosmologically privileged moment when the universe is still illuminated by countless galaxies visible in every direction. The KBC void reminds us that knowledge of the universe is not only spatially limited by our environment, but also temporally limited by our place in history. There is a window in which cosmic truth can be fully observed, and we are lucky enough to stand within it. That realization brings urgency to the present pursuit of cosmic understanding. If future civilizations inherit a darker sky with fewer clues, they will rely on the discoveries we make today to reconstruct the reality they cannot see. This sense of urgency inspires a generation of cosmologists to push observations to their limits, reaching beyond the void and into denser realms while time allows. The void also invites a deeper appreciation for the fragility of cosmic conditions necessary for life. In denser environments, galaxies endure frequent reshaping by mergers, violent starbursts, and massive radiation fields. Our quiet home offers stability. Here, stars like the Sun can shine peacefully for billions of years, and planets can orbit undisturbed long enough for complex biology to emerge. The void becomes not just a scientific feature, but a protective cradle. Perhaps intelligent life anywhere in the universe is more likely to arise in calmer regions like ours, places where cosmic chaos is muted. If this is true, then voids could be rare sanctuaries in an otherwise volatile universe. This idea reframes our perspective on existence. We are not in a dull, uninteresting part of the cosmos. We are in one of the few neighborhoods where living systems might have the time and stability to thrive. This aligns with the anthropic principle. We observe the universe from a location where observation is possible. Only in such serene places can thinkers evolve to ask cosmic questions. In that sense, the KBC void is part of our story, not a distraction from it. At the same time, the void challenges human intuition about what is normal. For generations, scientists assumed the universe must look similar everywhere, that our place could not be unusual. The void disproves that assumption. Rarity does not invalidate our existence. Sometimes the rare becomes reality. This realization opens new lines of inquiry. Perhaps the cosmos is filled with extreme contrasts, and our assumptions of uniformity have merely been conveniences. As we refine our models, we embrace the complexity of a universe far more varied than the simplified diagrams that used to appear in textbooks. The void's existence also sparks imagination about exploration beyond observation. Could civilizations someday traverse the boundaries of voids? Could future spacecraft navigate the gravitational flow lines toward denser superclusters? A journey across the void would take unimaginable time, but the possibility invites a grander vision of humanity's future. If our descendants ever venture into richer cosmic territories, they may witness environments dramatically different from our own. Brilliant cluster cores, starburst galaxies, and swirling flows of matter colliding at colossal scales. The contrast between their birthplace and the surrounding universe would reveal just how unique our current home truly is. Ultimately, the KBC void challenges us to think of the universe not as a static backdrop, but as a living structure that shapes the past, present, and future of cosmic knowledge. It reminds us that emptiness is not absence but influence, a force that can sculpt galaxies, alter measurements, sustain life, and direct our understanding. By studying the void, we uncover not only the nature of the cosmos, but the reasons we're able to contemplate it at all. In its silence, the void teaches that existence is a balance between what is there and what is missing. We are shaped by both. Our galaxy sails through a vast desert of space, and that desert, unexpected and profound, has given us stability, perspective, and the precious clarity to see the universe before the lights grow dim. In the end, the KBC void is a reminder that even in cosmic emptiness, meaning abounds. It tells a story about resilience and discovery, about how life can arise in the quiet corners of a grand and evolving expanse. It challenges us to embrace the beauty of rare circumstances, to value the knowledge we hold while the universe remains visible, and to continue exploring every horizon, no matter how distant or dark. The growing recognition of the KBC void's significance marks a turning point in humanity's ongoing effort to understand the universe and our place within it. It shows that even after centuries of inquiry, the cosmos remains capable of surprising us in profound ways. The void demonstrates that the universe is not a simple, evenly distributed expanse of matter drifting apart in perfect uniformity, but a richly varied landscape where environment shapes experience. Our home lies not within a bustling cosmic metropolis, but in a tranquil outpost on the edge of creation, a wide and quietly expanding wilderness. Far from diminishing our curiosity, this revelation only intensifies our desire to uncover the mechanisms governing the dark and luminous components of the cosmos. It motivates us to probe the universe more deeply, to refine our models, and to ask questions we never thought necessary, before we recognize that emptiness itself could alter our view of reality. This curiosity becomes the driving force behind next-generation missions designed to chart the universe with unparalleled precision. Space telescopes and terrestrial observatories will extend our reach to more distant galaxies, revealing the intricate details of the cosmic web beyond the void's outskirts. At the same time, theoretical advances will evolve as researchers test how dark matter, dark energy, and gravity interplay differently across contrasting environments. Cosmologists will integrate their findings to build a more comprehensive and flexible picture of cosmic behavior, a picture capable of accommodating rare structures like the KBC void without treating them as glitches in an otherwise flawless system. Indeed, one of the void's greatest contributions is how it encourages scientists to approach anomalies as valuable clues rather than mere outliers to be swept aside. Every surprising feature offers a chance to discover deeper truths about the universe's past and future, and the KBC void is perhaps the most powerful of such clues discovered in recent decades. It reminds us to question the default assumption that our environment is representative and warns us against the risks of generalizing from a single vantage point. This humility will guide future cosmology, fostering a more thoughtful interpretation of data that incorporates context and embraces the irregular. Beyond its scientific implications, the void also touches the human spirit, inviting reflection on the improbable nature of our existence. The calm emptiness around us may have been essential to the stability that allowed life to develop and persist long enough to gaze outward and wonder. If we had formed in a chaotic cluster where galaxies collide frequently and radiation storms rage, intelligent observers like us might never have emerged. In this way, the void becomes part of our origin story, not merely a backdrop but a contributing character. By offering shelter from cosmic violence, it has played a subtle but essential role in shaping the delicate structure of our world. That realization transforms what once seemed like a cosmic disappointment into a profound gift. We live in a region calm enough for reflection, yet open enough to provide views of the wider universe. The void around us has not isolated us, it has granted us clarity. Here, far from disruptive gravitational chaos, the night sky reveals the distant light of billions of galaxies still within sight. But this privilege will not last forever. As expansion continues to accelerate, many of those galaxies will eventually drift beyond visibility, leaving future observers trapped within a far darker horizon. We bear witness during a fleeting cosmic era when the universe remains decipherable on grand scales, when the fabric of the cosmos is still laid bare to those who seek to measure it. This realization should inspire urgency and gratitude to explore while we can, gratitude for the opportunity to know what exists beyond our own galaxy. The KBC void, once a curious footnote, now stands as a symbol of this moment in cosmic history. It compels us to continue mapping the cosmic web, interpreting the flow of galaxies, and searching for signatures of dark physics that could redefine our understanding of reality. It challenges us to broaden our perspective, to embrace the complexity of the universe's architecture, and to marvel at the elegance with which both matter and emptiness collaborate in constructing the world we occupy. If the universe is a vast and evolving tapestry, then the KBC void is one of its most captivating patterns, quiet yet impactful, rare yet fundamental, empty yet full of meaning. It whispers to us that where we are shapes what we know, and only by acknowledging the uniqueness of our viewpoint can we hope to discover universal truth. The pursuit of that truth continues, guided by curiosity that stretches farther than the galaxies themselves. We gaze into the silence of the void, not with fear of insignificance, but with appreciation of the extraordinary circumstances that allow us to exist and to wonder. In doing so, we affirm the greatest lesson the void has to offer, that even in the darkest reaches of space, discovery awaits those who dare to look deeper.